You might ask, why would we ever tackle the legendary Fibonacci sequence using the simplest tool in the programming toolbox, the humble if-else statement? Well, it's because simplicity is how learning begins. Sure, it's like trying to perform brain surgery with a butter knife. Possible, but not exactly efficient. Still, everyone has to start somewhere. The beauty of if-else logic is that it mirrors how our brains naturally approach decisions. If you're hungry, then eat. Else, complain about being hungry anyway. In coding, if-else works exactly the same way, translating common sense into something a computer can understand. Let's remind ourselves what the Fibonacci sequence actually is. F of 0 equals 0 and f of 1 equals 1. These are the base cases, our starting points. For all other numbers, the rule is f of n equals f of n minus 1 plus f of n minus 2. Here's the Fibonacci definition translated into pseudocode function Fibonacci of na. If n equals 0, then return 0, else if n equals 1, then return 1. Else return Fibonacci of n minus 1 plus Fibonacci of n minus 2, end function. Imagine calculating Fibonacci of 4. Start. Fibonacci of 4 needs Fibonacci of 3 plus Fibonacci of 2. Fibonacci of 3 then splits again into Fibonacci of 2 plus Fibonacci of 1. Fibonacci of 2 splits further into Fibonacci of 1 plus Fibonacci of 0. We hit the base cases. Fibonacci of 1 equals 1, Fibonacci of 0 equals 0. Fibonacci of 2 equals 1, which is 1 plus 0. Fibonacci of 3 equals 2, which is 1 plus 1. Fibonacci of 4 equals 3, which is 2 plus 1. Looks straightforward, doesn't it? But there's trouble lurking beneath that simplicity. Here's the dark side of this elegant recursion massive redundancy. For example, calculating Fibonacci of 5 means Fibonacci of 3 gets calculated twice, Fibonacci of 2 3 times, and Fibonacci of 1 5 times. Imagine going to the supermarket 5 times because you keep forgetting milk. That's exactly what our recursive if-else code is doing. In computer science, we measure efficiency using complexity. Time complexity, it's O of 2 to the power of n calculating. Fibonacci of 30 means over a billion operations. Space complexity, O of n. Each recursive call adds another stack layer. Too many and your computer simply gives up. Could we avoid recursion completely with if-else? Technically, yes. Function Fibonacci simple n. If n equals 0, then return 0, else if n equals 1, then return 1, else if n equals 2, then return 1, else if n equals 3, then return 2, else return panic underscore and underscore run underscore away, end function. See the issue? You'd have to manually enter every number forever. That's not programming, that's punishment. So why teach recursive if-else at all? It shows the link between math and code. It introduces recursion naturally. It highlights why efficiency matters. It teaches computational thinking. It's a starting point before exploring smarter solutions. Think of it as letting kids touch a hot stove once. Painful but unforgettable. In short, recursive if-else solutions directly reflect mathematical logic. They're intuitive and beautiful, but also disastrously inefficient. Recursive redundancy escalates quickly, but it's an invaluable teaching tool. In our next video, we'll leave this recursive disaster behind and look at a sensible alternative, iterative solutions using loops. It's faster, smarter, and doesn't make your computer question its purpose in life. Stay tuned for Fibonacci meets loops. Finally, a solution that makes sense.